welcome back. So, from now onwards, we will move on to module 2. Under module 2, we will cover topics such as capillarity, surface tension. Okay, we will look at various measurement techniques that are available to determine surface tension. If we know contact angle or contact angle, if we know surface tension, right? Apart from that, we will also try to understand some of the fundamental equations like Young-Dupré, Young-Laplace equation. Okay, and after that, we will look at the application of Young-Dupré and the application of Young-Laplace equation. Okay, and but in this lecture, we will look at the capillarity and surface tension. We'll look at the we'll see what is surface tension and how it is defined. Okay, and after that we will see from thermodynamics perspective how we can define surface tension, right? And then after that we will look at we have some tutorial session also. So we'll try to solve a small problem exercise, and after that we look at the types of various types of contact angle measurement techniques. We will not describe them in detail, but we'll try to list them in today's lecture. Okay, right. Let's begin our lecture. Right. So first of all, let us first understand what is capillarity. So capillarity is regarded as a consequence of surface tension. Okay. We're going to look at the capillary rise. Okay, so capillary rise is due to the upward movement of the liquid. Okay, through the narrowed space. Okay, the process by which liquid climbs up the surface through a narrowed, a narrow space or the porous channel. Right. It is due to manifestation of forces of cohesion, adhesion and surface tension. Okay, surface tension and capillarity both go hand in hand because capillarity is regarded as a consequence of surface tension, right? In this lecture, we are going to look at first what is known as surface tension. Okay, and I'm going to briefly touch upon from the thermodynamic perspective, how we can understand surface tension, right? And we're going to look at combined first and second law of thermodynamics. So from combined first and second law of thermodynamics, how we can define surface tension, right? And after that, we'll solve a small exercise. We'll see a small exercise and we'll try to, calculate the specific surface area from a given image, right? Yeah. So first, let us understand what is surface tension. So it is basically nothing but cohesive energy per molecule. Let's say let's assume that the molecules in the bulk. There are molecules in the bulk. Okay. These molecules are if you look at in the bulk, the molecules are surrounded by each neighboring molecule, right? So there will be interaction from all the neighboring molecules from all directions, right? 360 degree, right? And since all the neighboring molecules interact and there will be a pairwise interaction between all the molecules, we can understand that the interaction of that. Okay, the cohesive energy per molecule in bulk, let's say we denote it as U. Okay, right. Now, similar case, if we take a molecule and assume that the molecule is at the interface. Now, at the interface, there is a shortfall of energy. Okay, there is a shortfall of energy. It's because there are two adjoining phases here. One is the subphase, which is nothing but let's say we talk about water air in this case. you create a water air interface in this case because your surface is water. Okay, we're talking about water air in this case, right? Now, so since part of the molecule is exposed to water side and the remaining part is exposed to air side, so the part exposed to air side, loses contact with its neighboring molecules, right? Okay, so the interaction in this case is expected to be less than the interaction in the bulk. Okay, so this shortfall of energy, okay, leads to the changes in the net. So there will be net imbalance in the force, okay, which cause the molecules to minimize their contact area within the adjoining bulk phase, right, which is air in this case, so that there will be a downward force, okay, and that is nothing but the force will be acting downward in this case because they want to maximize their contact area within the the surface, okay, so that they will get more contact with their own molecules, okay. So in such way, in such case, you would expect that there will be a net imbalance in the force. So eventually, force will be acting downward, which is nothing but surface tension in this case. Okay, so you can understand in this way also the cohesion energy per molecule. They say if molecule is confined in the bulk, the cohesive energy of molecule, energy per molecule is U. If you denote that as U, then we can say that the cohesive energy of molecule at the interface is U by 2. Okay, this is because of the shortfall of energy. In the absence of neighboring molecules, the molecule experience net imbalance in the force, and that is acting downward because they are they want to maximize their contact with their own neighboring molecules. So this is nothing but surface tension. Okay. So in a nutshell, you will have at the surface, okay, at the interface, there will be force, line of tension, okay, along the length of the surface, okay, because of the shortfall of energy, okay. So that's why it is often expressed in terms of Newton per meter, unlike pressure unit. This is always expressed in force per unit length, right? Length of the surface, right? So because this is acting at the surface, right? The shortfall of energy is due to the molecule because some of the molecules are confined at the interface, correct? Right. So we can also get more insight into the surface tension. Okay, so now let's ask a question. So is this going to be the same in all in different kinds of, in different types of interfaces as well? For example, let's say in this case, you have taken an example of air-water interface. What if I replace this air with some other fluid, okay, or some other liquid? Say, for example, I replace air with oil like a substance. So you will have a two immiscible mixture. One is water and the another one will be oil. In this case, what will be the surface tension? Okay, so the surface tension in this case will be drastically different. It is because of the interaction between the molecule, okay, at the interface. So they are experiencing, they are exposed to two different adjoining phases, right? So the neighboring molecules are entirely different. Okay. So in the case of water air, the surface tension is little larger than any alkane water system. Okay. So here it is 72 millinewton per meter. At same temperature, if you measure for oil water, it is 20 millinewton per meter. Okay. The difference is due to the different types of interaction. In the case of air-water interface, there is significant increase in surface tension. in the case of air-water interface, it is because of the hydrogen bond, hydrogen interaction, right? Hydrogen bond interaction. Whereas in the case of oil, water-oil interface system, it is because of the Van der Waals type interactions. So because the as the types of as the molecules type changes, the interactions that come along with the molecules also changes, because of which the surface tension values also goes down. Okay, changes drastically, right? So this is nothing but surface tension. Now we look at so we can also relate surface tension with respect to work done. Okay, let's imagine we have. Let's imagine that we have filled, in a container. We pour water and fill the container like this. Okay, right. Now at the interface, right, between water and the air, I place a very thin wire. Okay, very thin wire at the interface. Maybe I can draw something like this, right? Very thin wire. Okay, it is very light in weight, so it floats. It doesn't sink, and it doesn't settle. It doesn't sink in the water, so it just floats at the surface. Now, this wire is very, tiny and very light in weight. So you know that there is surface tension acting along this thin wire at the interface. So eventually, what happens, because this water molecule tries to maximize their contact area, so there will be a net imbalance in the force. There will be force in the downward direction. So this surface tension will pull this wire downward, right, in this way, right? So if we assume that at time t equal to 0, this thin wire is placed at the interface. Maybe after some time, if you look at this thin wire would have been displaced a bit from the surface. Okay, in the z direction. Okay, if there will be small displacement. At the surface because of the surface tension. Now this is at any t, right? So the thin wire would have moved in the z direction downward. Okay, so small displacement would have happened because the surface tension pulls the thin wire downward, right? So now we know that some work is being done by the system in this case. Now we can relate this work with respect to, with the surface tension. So one can say that if I apply equal amount of work, okay, and then I can bring this wire back to its original position. That means the work done in this case is nothing but gamma into d, correct? Because we know gamma is surface tension. Now the surface tension, and the product of surface tension and the change in area should give us the work done, right, by the system in this case. Or you can impose equal amount of work so that you bring this wire back to its original position. So in this case, we can relate the work done with surface tension in this way. So work done is nothing but gamma into dA in this case, right? Now we can also define gamma from the thermodynamic perspective. Let's say we know that G, which is Gibbs free energy, is function of temperature, pressure, composition, and area. By employing the total derivative approach, one can get in this the equation in this differential form. Right? And then we know that these partial derivatives, all these partial derivatives, right? So this is nothing but chemical potential, right? And this is nothing but molar volume, and this is nothing but entropy, right? But if you impose a condition that at constant temperature, okay, and constant pressure, and for a pure substance, change in number of mole is also 0. In such case, you would expect that you would get dG as simply nothing but dou G by dou A, T P N dA. So this partial derivative is defined. We denote this partial derivative as gamma, right? This is nothing but surface tension. Okay. So you can also define surface tension in this way. That is, surface tension is nothing but dou G by dou A, okay, at the constant temperature, pressure, and constant temperature and pressure for a pure component. You can even say that constant N, right? Right. So now we can even look at from the combined first and second law of thermodynamics, how we can get the definition for surface tension, right? We know the first law of thermodynamics and we know second law of thermodynamics. Now, by using combined first and second law of thermodynamics, can we get the relationship for surface tension, okay, with Gibbs free energy? The same partial the same relation that we get when we try to derive using combined first and second law of thermodynamics, right? Yeah. Now we will look at how we can define gamma. Okay, so we know from our first law of thermodynamics, we know what is du, which is nothing but del Q plus del W. Okay, so this is our first law of thermodynamics. For a closed system. Now, if I expand this, I know for reversible system, del Q is nothing but TdS, okay? And then I'll simply write this del W as it is. Now, here, because, so this comes from the second law of thermodynamics. So the relationship for del Q comes from the second law of thermodynamics. Now, we can call this equation as combined first and second law of thermodynamics. Okay, right. Now, del W in this case, we know that it is nothing but, del W PV, right? Plus del W non-PV work, right? We have two kinds of work. So del W total is nothing but del W, which is nothing but PV work as work associated with the PV term, work associated with the non-PV term, right? So this is something we know already. So if I substitute this into this equation, then I will simply get this way. Okay. Right. So I know for reversible system, del W, the work associated with the PV term is nothing but minus PdV plus W. Okay. So this minus takes care of the suitable sign convention. That means if work is done by the system, it should be negative, then on the system should be positive. So this minus takes care of that sign convention. So we can simply write the work associated with the PV as minus PdV itself. So this is equation number 1 for us. Now, we also know our Gibbs free energy equation, which is nothing but dG is nothing but H minus Ts, right? This is what we know. G is equal to H minus Ts. Now, if I differentiate this, I would simply get d of h is nothing but u plus pv minus this. If I differentiate, I would get s dt minus t ds, right? This is what I will get. So if I split this into 2, which is du plus d of pv, which is again du, I know, that is tds minus pdv plus del w non-pv, okay, plus pdv plus vdp minus s dt minus tds. So if we expand this equation, we will get the terms, different terms like this. Now what we can do is, we know there is TDS, this for and TDS plus and minus TDS both get cancelled, and we have minus PDV and plus PDV both get cancelled. Now if we impose a condition that at constant temperature, okay, at constant temperature and pressure, so we will simply get del W non-PV. Okay, so remember, surface tension is work done non-PV, work done associated with non-PV. Okay, so we can we also know del W non-PV, which is nothing but gamma dA, right? So now we can simply say dJ is nothing but gamma dA, okay? Or we can even say gamma is nothing but dou G by dou A at constant temperature and pressure. All right, so we know the relation from the both way. We can relate. We can find gamma as gamma is nothing but dou G by dou A at constant temperature and pressure. Now we will look at the different types of measurement techniques, right? Techniques that are available to determine surface tension. Okay, so we are going to. There are, at least there are. A couple of them is quite often used. Okay, but many are being proposed by at different. From time to time. So we can list. We can name some of them here. We have what is known as Wilhelmine plate and maximum bubble pressure, spinning drop, Duvernay ring, capillary rise, pendant drop method, and so on. Although there are many more techniques available, we are only listing few of them. Okay, which are quite familiar, right? So among this, we will discuss the Wilhelmine plate and capillary rise, okay, in detail, right? And the Wilhelmine plate and Duvernay ring both works on a similar principle. Only the geometry are different. Okay, geometry is different. So we will see the principle of Wilhelmine plate and capillary rise in next video lecture. But at least we should know there are different techniques available to measure surface tension if we know what is contact angle, or contact angle if we know surface tension. So contact angle is the angle established by liquid on the solid surface. You say we're talking about solid surface. Okay, a simple solid, and on top of which you have a liquid drop. If I place a liquid drop, okay, or if I spread a liquid on top of the solid surface, whether liquid will completely wet, okay, whether the liquid will completely wet, okay, or not, depends on the contact angle established by the liquid with the solid surface. Okay, say for example, so liquid may be partially wetting, which means that they will be spreading to some extent, although they are not completely spreading. In such case, you would expect theta to be less than 90 degree. Okay. Whereas on the other hand, so the drop may not spread. Okay. They may want to they may detach from the surface. They may want to detach from the surface. In such case, it will it will establish theta, which may be greater than 90 degree. So something like this. Okay. So in such case, theta may be greater than 90 degree. So in very, there are there are many macroscopic applications where the properties, macroscopic properties, are governed by microscopic properties like surface tension theta, which we will see in detail later, right? So now we'll move on to the small exercise. We'll try to do some small exercise in this tutorial. Let's say we have scanning Newton microscopic images, and what you see here is the silica particles, right? So there are a number of silica particles, and you can see the scale bar at the bottom of this image, which says that the scale bar of this length is 5 micron. Okay, so if I place this scale bar and try to fit in this particle, I can actually calculate or reduce diameter or size of the particle. So in this way, one can do reduce diameter for for large number of particles, and try to take the average out of that. Okay, so if one does for a large number of particles and get the average, that will be that we have. We can even report along with the error also, right? In such case, so let's say in this case, the average size of the silica particle is, let's say, 4 micron, the diameter. The radius of this will be 2 micron. Okay. So we know for a spherical particle, the specific surface area is nothing but 3 by rho into Rs. Okay. Now we know what is radius in this case. The density is approximately 2. Okay, 2000. You can say in terms of SI unit, it is 2000 kg per meter cube. Into radius will be 2 into 10 power minus 6 meter. Okay, so eventually what you will be getting here is meter squared by kg, right? Yeah. So if you simply calculate this, it will be simply 3 by 4 10 power 3, 3 by 4 10 power 3 meter square by kg. Okay, meter square by kg. 3 by 4 is simply 0.75. You can also say it as 0.75 into meter squared by gram. Okay, either it is 0.75 into 10 power 3 meter square per kg or 0.75 into meter square per gram. So in this way, also you can calculate the specific surface area of a given particle. So we've done a similar problem in our module 1. Okay, for different geometry, right? So this will be based on the scanning Newton microscopic images. So can we calculate? So here we ask the question like, can we calculate what is the specific surface area in this case? So we'll stop here and we'll continue from the next lecture. Thank you.